Welcome back to Calculus 1. Up until this point, we have relied heavily on graphs and numerical tables to estimate limits. While visually intuitive, these methods are notoriously imprecise and computationally exhausting for complex functions. Furthermore, as we learned with the epsilon delta definition, true mathematics demands rigorous algebraic certainty. Today, we transition from estimation to exact calculation by introducing the properties of limits, also universally known as the limit laws. These laws form a bedrock theorem that allows us to deconstruct massive, terrifying algebraic expressions into tiny, manageable pieces. Before we unleash these laws, we must state a critical prerequisite. Suppose that the limit of f of x as x approaches a exists and equals L, and the limit of g of x as x approaches a also exists and equals m. The laws we are about to learn are absolutely dependent on these individual limits existing. If they do not exist, the laws immediately shatter. Let's establish our first tools, the linear properties. First, the sum rule states that the limit of the sum of two functions, f of x plus g of x, is exactly equal to the sum of their individual limits, L plus m. Intuitively, the limit of a sum is the sum of the limits. Naturally, the difference rule closely follows. The limit of f of x minus g of x is simply L minus m. Next is an incredibly useful property called the constant multiple rule. Let C be any real number constant. The limit of a constant, ce multiplied by f of x, perfectly equals the constant c multiplied by the limit of f of x, which equals c times L. Essentially, you are fully authorized to pull constants straight out of the limit operator. Let's do a fast example. Evaluate the limit as x approaches 2 of 5x. By pulling out the 5, we have 5 times the limit as x approaches 2 of x. The limit of x as x approaches 2 is simply 2, so the final answer is exactly 10. Now we scale up to multiplication and division. The product rule elegantly declares that the limit of the product f of x times g of x is equal to the product of their limits, L times m. The limit of a product is the product of the limits. The quotient rule is similar but desperately requires a massive warning label. The limit of f of x divided by g of x equals L divided by m. However, this is strictly true if, and only if, the limit of the denominator, m, is absolutely not equal to 0. If the denominator approaches 0, this law immediately fails and requires advanced algebraic manipulation, which we will conquer in future lectures. Finally, the power rule. If n is a positive integer, the limit of f of x raised to the power of n perfectly equals the limit L raised to the power of n. You can confidently pass the limit directly inside the exponent. This rule also universally extends to roots, provided the root is mathematically defined. Let's wield all these laws simultaneously by attacking a full polynomial. Let's rigorously evaluate the limit as x approaches 4 of the quadratic polynomial, 2x squared minus 3x plus 5. Normally, students just plug in the 4, but we must prove why that is strictly legal. First, we apply the sum and difference rules to shatter the polynomial into 3 separate limits, the limit of 2x squared minus the limit of 3x plus the limit of 5. Next, we aggressively apply the constant multiple rule, pulling the 2 and the 3 outside their respective limits. Now, we use the power rule on the x squared term, bringing the limit inside the square. Finally, we evaluate the raw base limits. The limit of x is 4, and the limit of a constant like 5 is just 5. Plugging these base values back in, we get 2 times 4 squared minus 3 times 4 plus 5. This simplifies precisely to 32 minus 12 plus 5, resulting in a perfectly rigorous final answer of 25. For our grand finale, let's demolish a complex rational expression. Find the limit as x approaches negative 1 of the fraction, numerator x cubed plus 4x squared minus 3, denominator 2x plus 5. First, we aggressively invoke the quotient rule, the limit of the top divided by the limit of the bottom. However, we must immediately verify the denominator. The limit as x approaches negative 1 of 2x plus 5 is exactly 3. Since 3 is strictly not 0, the quotient rule securely holds. Now, we apply the sum, constant multiple, and power rules to both the numerator and the denominator simultaneously. The top becomes negative 1 cubed plus 4 times negative 1 squared minus 3. The bottom becomes 2 times -1 plus 5. Simplifying the arithmetic, the numerator is -1 plus 4 minus 3, which equals exactly 0. The denominator is -2 plus 5, which equals exactly 3. 0 divided by 3 is purely 0. The calculation is impenetrable, and our limit is exactly 0.